Science 20, we talk about temperature. Okay, it's all about temperature, and we talked about the kinetic molecular theory just recently. We're going to talk about temperature, the different measurements of temperature, again, what temperature means, and different things like that. So this is Chapter 8 in the textbook, Heat Physics, that we're using, page 228. Temperature. Temperature is a measure of the average kinetic energy that is within an object, or that an object possesses. Average kinetic energy. Remember, we talked the kinetic molecular theory that all particles are always moving, right? Well, in solid form, we said that the particles really aren't moving that much. They're just kind of vibrating, and they're holding a fairly rigid sort of shape and structure. Well, if we increase the temperature of solid ice, as an example we used, then the particles gather more energy, right? And they start to change state at a certain temperature. Now, the temperature that a solid water turns to liquid water, what's that temperature? You guys all should know the temperature. Ice turns to water at 0 degrees Celsius, okay? 0 degrees Celsius. So when the average kinetic energy of all the particles of water, if they're in an ice cube or a block of ice, when the average kinetic energy is 0 degrees Celsius, then those particles start to break away from each other and become liquid. All right? Now, some of the particles may have far more energy than that, and some may have far less. But the average is what we call the temperature. The kinetic energy, okay, is the measure of how much energy an object has, how much energy, due to the movement, from the movement of its atoms and molecules. Okay? So what is kinetic energy? We're talking about average kinetic energy as temperature. Kinetic energy is the energy from movement of the particles. There are different units for measuring temperature. And a couple of these units, well, the first one for sure is the unit for temperature that we are most familiar with in Canada here. And globally, Celsius is sort of an international unit that you would hear in most places in the world, right? The scale, the Celsius scale, is based on the properties of water. 0 degrees Celsius is chosen to be 0 because that's when water freezes or ice melts. Okay? So that's why 0 is 0. Do you ever wonder that? Do you ever think, oh, that's a strange coincidence that water, melts at 0 degrees? That's really cool. Well, that's kind of how they set up the scale. When water melts, that's 0 degrees Celsius. When water boils, it's at 100 degrees Celsius. Okay? Now, there are conditions that would change these temperatures, like pressure, right, and all that sort of stuff, that water might boil at a little bit different temperature, but on standard conditions, at sea level, standard atmospheric pressure and that sort of thing, pure water would boil at exactly 100 degrees Celsius. So that's the basis of the scale, is on the properties of water. And then basically everything in between 0 and 100 is split up 100 ways, right? So 1 degree Celsius is 1/100th of this change between where water freezes and water boils. So 0, 100. Now, before we get to this unit right here, what's the other common unit that is used, especially in the United States? Yeah, degrees Fahrenheit. Degrees Fahrenheit's a little bit different, and I have a chart here, which is really small. I'm going to enlarge that in a second. But degrees Fahrenheit, I don't know if you guys have ever noticed, when it's 0 degrees Celsius, what is the temperature in Fahrenheit? Yeah, it's 32 degrees Fahrenheit when water freezes. Okay? Water freezes. And then water boils at, it's right down here, 212 actually, 212 degrees Fahrenheit. So, as you notice here, between 32 and 212 is the exact same temperature change from 0 to 100 degrees Celsius. Each degree Fahrenheit is quite a bit of smaller difference, okay? each degree Fahrenheit is quite a bit smaller than each degree Celsius, because there's a lot more degrees Fahrenheit between when water freezes and when water boils. You see that? So there's more here. What is this? 180? 180 degrees in Fahrenheit instead of 100 degrees Celsius. So each degree Fahrenheit is smaller. Now let me see. I was having trouble enlarging this before. Okay, it likes to go that way, but oh wow, look at that's really cool. Okay, I don't know if that's helping much. Not too much. Those of you in the back section there might not be able to see that very well. But let's just go over this here real quick. So here you see water freezes. Okay, that says water freezes. Here's Celsius and here's Fahrenheit. So that is 0 degrees Celsius and 32 Fahrenheit. 212 is when water boils, and 100 degrees is when water Celsius is when water boils. Now I'm going to talk about this in a second, these temperatures down here and why they're important. But let's talk about Kelvin, okay? The Kelvin scale for temperature. Now I want you to notice one thing, that when we're talking about kelvins, we don't say degrees Kelvin. Okay, it's hard not to, because it's degrees Celsius, degrees Fahrenheit. It's not degrees Kelvin, it's just kelvins, okay? You don't have a little degrees sign before the K. Now, the Kelvin scale is the preferred scale for science, okay? And I'll tell you why in a second, but one important thing to note is that the units, so each Kelvin is the same size as a degree Celsius, okay? So that's the first thing you want to make sure you have. Each Kelvin, each 1 Kelvin is the same size, is the same amount of change of energy as 1 degree Celsius. Okay? So if you increase 10 degrees Celsius, that's the same as increasing 10 Kelvin. Now why do we have this other scale? Because Kelvin temperature is based on absolute 0. Absolute 0. So 0 Kelvin, that's not okay, that's 0 K. 0 Kelvin is the point, the temperature, in which all atomic motion stops, even the slight vibration. Okay, it's so cold that everything would just freeze up solid. It would totally stop. And it's interesting to note, and I remember I had trouble with this when I was your age, but there is no temperature colder than 0 Kelvin. That's why it's called absolute 0. And you may think, well, how is that possible? What if you go to Pluto? Isn't it colder than 0 Kelvin there? It's not actually. Because if you think about it, heat is energy, right? And so you can remove energy until all the energy is completely gone. Then you can't remove any more, right? It's like if you shut off all the lights, okay, and close all the blinds, you're removing light from this room. If you got to a point where all the light was gone, you couldn't take any more light out of this room. You couldn't block any more light. You know what I'm saying? It's completely dark. If you have total and utter darkness, there's no more light to take out. So there would be a rock bottom. The high end of the scale, well, you can keep adding more and more energy. So there's really not a top of the scale, but there is a bottom. So down here, if we go back to here, absolute 0 is 0 Kelvin. And that temperature in Celsius is negative 273 degrees Celsius. So absolute 0, I'll just rewrite that so it's a little bit bigger for you. But absolute 0 is negative 273 degrees Celsius. And it's, just for curiosity here, you won't need to really use this, but it's negative 460 degrees Fahrenheit. So absolute 0. That's 0 Kelvin and negative 273, technically 0.15. All right. So water freezes at positive 273.15 kelvins. That is the same as 0 Celsius. So I know you'll need to take some time to kind of digest this. What you're going to want to do is make sure that you have, and I would suggest drawing these two little temperature thermometers here, and just drawing sort of the parallel degrees between Kelvin and degrees Celsius at least. Fahrenheit's not as important, it's just for reference sake there. So 0 Kelvin, absolute zero. The advantage of the Kelvin scale, and the reason why it's so popular in science and used so widely globally, is because there are no negative numbers. If 0 Kelvin is actually absolute zero, then there's nothing below that. There's no negative numbers. And as I mentioned, 0 Kelvin is the coldest temperature that's possible. All energy is removed. No kinetic energy in the atomic level whatsoever. So if you don't have this down already, 273 Kelvin is 0 degrees Celsius. And negative 273 degrees Celsius is 0 Kelvin, which is absolute zero. A couple more temperatures. If you want to put them on your thermometers, you can. It doesn't really matter. But room temperature is about 25 degrees Celsius, right? 24, 23, 25, somewhere around there. And that would be 298 Kelvin. Okay? About 298. That's 273 plus 25. The boiling point of water is at 373 Kelvin, and you do see that on this scale too. Okay? Okay, so the Kelvin scale is probably something new to you. And when we do our calculations, so in this heat unit, we're going to do some calculations, kind of like we did in the other parts of physical science with the mirror equation, stuff like that. But there will be some calculations, and the temperature that you're going to use will, in lots of cases, not every case, but lots of cases, will be Kelvin. There are some where we use Celsius, of course, but okay. All right, so moving on here, if you've got most of that, I'll just bump this down a little bit. Recall from section 8.1 that temperature and volume are related. Now think about the balloon here. If we have a balloon full of air and we heat up that air, then the molecules in the air are going to move faster, and they're going to bounce harder on the sides of the balloon, and they're going to want to occupy more space, and so the volume is going to increase. With gases, as the temperature goes up, atomic motion increases, and as that atomic motion increases, the volume also increases. So that's just the last little point. As the motion of the particles increases, the volume would also increase. And the little note under the figure says, moving gas particles, they push on the walls of their container. So it increases pressure as well, and if that volume can change, the volume will expand to maintain the pressure. As they warm up, they move faster, the particles spread out, inflating the balloon. Alright, so thermal expansion in 8.3. We've talked already about how adding energy to atoms in a material make them move around more and more. We've also talked mostly about gases and stuff. But on a practical level, when we heat up most materials, they expand. And if we cool them down, they contract. So if we take a look at metal piping or railway ties, the metal pieces, and how many of you have ever noticed in a bridge? On a bridge, there is usually a section at the beginning and the end of the bridge where there's metal, kind of a metal section where there's interlocking teeth on bridges. I don't know if you ever noticed that. But those would be expansion joints because the steel structure or the steel parts of even the concrete and stuff like that, when temperature changes wildly, like in Saskatchewan here, materials expand in the heat and contract in the cold. And so, a lot of times, even bridges, you'll see that, there'll be more space in the winter in these contraction joints, and in the summer there won't be very much space at all because everything expands. So I know I showed you this video here. Just going to watch this video again. And where would it go? Right here. Okay. So here are two pipes, and notice that they're getting closer together. As the temperature rises, there is expansion, and each part of the pipe expands towards the other section. As the temperature drops, there's space again. So as you can well imagine, if you become an engineer or something like that, this is very, very important. Okay, if you're designing bridges, or if you're putting pipe together, you're designing, some kind of aquatic system or anything like that, you need to understand expansion of metals, so that there's obviously there needs to be some room for this expansion to safely happen. So if we go back to our notes, anybody have any questions? All right. So the change in size, okay, if we're talking about an expansion due to temperature change, the change in size happens in all dimensions or in all coordinates, but we are going to examine just one coordinate since it's easier for us to measure. We will consider linear expansion, okay, which is the change in length. So this is what we're going to study. These are the questions, the calculations we're going to do is linear expansion, change in length due to temperature change. For most solids, the change in length is directly proportional to the change in temperature. So change in length is directly proportional to the change in temperature. So that means for each material, there is some sort of special constant that says, hey, when we increase the temperature by 1 degree, let's say, a certain amount of substance should increase in length by a certain bit. And it should happen every time. It should be fairly predictable. So here's the formula for linear expansion. Change in length equals, and this is the Greek letter alpha, and we're going to find out that that's a special coefficient. L naught, or L0, that's going to be original length. Delta T is the change in temperature. So copy that formula out, and then you're also going to want to just make little notes here about what each of them represent. Now, for some reason, I'm missing a T there. But change in L is the change in length in meters. This alpha is the coefficient of linear expansion. And the unit's not as important, but it's per degree Celsius. That -1, as you know, that those of you in math, brings that down to the denominator. So that's per degree Celsius. So for every degree Celsius, there's a proportional change in the length. And this L naught, or L0, the original length in meters. I think something happened to my formatting. I'm missing H's here. And delta T is the change in temperature. And because Celsius is used most commonly, it's mentioned in Celsius. But we know that the change in Kelvin is the exact same as the change in Celsius. So you can put in Celsius here, or Kelvin. Or kelvins. Okay? So you don't have to do the conversion to Celsius if you have a change in kelvins. It's the same thing. Okay, so that's the change in length, and that's for solids. Liquids also undergo expansion. But since they more readily change shape, we measure the change in volume and not length for a liquid. So we measure the change in volume, and that formula, if you notice, is extremely similar to the change in length. It's just change in volume equals, this is beta, which is another Greek letter, alpha, beta. Actually, if you haven't put this together before, the first two letters in the Greek alphabet are alpha and beta. That's why we call our ABCs the alphabet. It's like you get to know your alpha betas when you're young. Alphabet, alpha, beta, alphabet. Get that? Yeah, lights going on all over the room here. Yeah, pretty cool, eh? All right, so V naught, or V0 here, that's original volume, and of course change in temperature as well. So just take a minute to copy this out as well. All right, sample problem, page 231 states, a steel I-beam is used for construction of a bridge, and it's 9.2 meters long at 20 degrees Celsius. On a hot summer day, the temperature rises to 40 degrees Celsius. What is the change in length of the beam due to linear expansion? So what we want to do is we want to, when we unpack any problem, we want to write down what we're given and what we need to find. Okay? So I want you to, I'm going to model this for you. I want you to write down, basically almost exactly what I write down so that you can know what I'm expecting and how to organize your material here, okay? So this 9.2 meters long, okay, that is initial length. Now what you might want to do is you might want to put this together right away and say, hey, I am going to need to use this formula, and so I am going to label everything that I'm given in the question, and I'm going to figure that out. So the original length is L naught, right, or L0, or L original. So that's 9.2 meters. Okay? The temperature rises from 20 to 40 degrees. So if we go back and look at our formula here, which part of the formula would that tell us about? Okay, triangle T. Yeah, that's actually another Greek letter, delta. So we have alpha, beta, and delta. Okay, that's delta. So we say delta T. You might hear some people say triangle T. I don't hear that very often. You should say delta T, and what it means is change in temperature. Okay? I've been to a few universities and I've heard triangle T, but it's not good. Okay, so delta T is going to be what? 40? 20. Okay, is that this one right here? Or where'd you get 20 from? Thank you. Remember, change in temperature is the final temperature final, minus temperature initial, which in this case is 40 minus 20, so that's 20. Okay, delta T is 20. Okay? Very good. So what is the change in length due to linear expansion? So we're looking for the change in length. And this is what I do. This is what I think is a good idea for you to do, but change in L equals question mark or some unknown or whatever. Tell yourself what you're given and what you need to find. Now, of course, we're going to use this formula like we had mentioned, right? Delta T. What do we need to, okay, we're going to find delta L here, the change in length. I'm given this, I'm given this. I'm missing this, right? Okay, so this is where you look in your textbook and you look at the chart of coefficients of linear expansion. So go ahead and do that. It's on page 231. All right, so we saw in the chart that the coefficient of linear expansion is, what does it say, Steele? 12. 12 what? It's not 12 meters, and it's not actually just 12. Look carefully at the chart there. Times 10 to the negative 6. Okay, everyone listen. Everyone listen. If you put just 12 in for alpha, you're going to have big problems, right? You can totally wrong number. So in that chart, they just list these numbers, but at the very top, they say, hey, remember that it's times 10 to the negative 6. So you can't forget that stuff. All right? So we'll get that straight. Okay, as we continue on here then, delta L is 12 times 10 to the negative 6. The original length is 9.2. Make sure your units line up, right? This is per degree Celsius. This is meters. And temperature is degrees Celsius. And our change in length is going to be then in meters, right? The units are going to have to line up. See that? Okay, so change in temperature and then is 20. So, multiply all these together, what do you get? All right, when you multiply those three numbers together, you get this, 0.002208. Now, what is the length in what units? It's meters. Because remember, this was degrees Celsius to the negative 1. This was meters. This was degrees Celsius. So the Celsius cancel out, and you're left with meters. Now, the reason why, you asked why this is such a small number, is because it doesn't change length very much. I mean, it's a very, very small change. If you think about it, it's just because it's warmer, right? So a 9.2 meter long I-beam is going to change 0.002 meters. So if I multiply this by 1,000, 2.2, what unit is that? That's millimeters. So do you see how a 20-degree change, which actually isn't that much, right? I mean, temperatures can change 80 degrees here in Canada, right? Like in Saskatchewan, where we are. So you think 20 degrees, that's not much. 2.2 millimeters, now that's a pretty small amount, right? But that's a big deal when you're constructing a bridge, right? And if it's a longer beam, if this length right here, the original length, is quite a bit bigger than 9.2 meters, then you're going to get quite a bit more expansion. So that is a small amount, but it can make a big difference.